Welcome to this tutorial on hypothesis testing. Hypothesis testing is a statistical method used to make decisions about a population parameter based on sample data. Today we'll be testing a claim made by a fitness app that the average user exercises for 30 minutes or less per day. To test this claim, a random sample of 50 users is collected. Their mean daily exercise time is 32 minutes. The standard deviation of exercise time for all users is 6 minutes. Since the standard deviation is for all users, it is a population standard deviation sigma. We want to test if the claim is incorrect at the 3% significance level, that is, at alpha equals 0.03. Now, the claim is that the average user exercises for 30 minutes or less per day. Testing if this claim is incorrect means testing if the average user exercises for more than 30 minutes per day, or mu greater than 30, where mu is the population mean. This then becomes the alternative hypothesis HA or H1 since it has no equality. Recall that the alternative hypothesis can only take on less than, greater than, or not equal to signs. The null hypothesis H0 will be that the average user exercises for 30 minutes or less per day since that statement contains equality, or simply because the less than or equal to sign complements the greater than sign in the alternative hypothesis. Note that some always use equal sign for the null hypothesis irrespective of the sign in the alternative hypothesis. But in this video we will keep the null as mu less or equal to 30. This is a one-tailed test, specifically a right-tailed or upper-tailed test. Note that we use the alternative hypothesis to determine the direction of the test. Now, since the population standard deviation is assumed to be known, we conduct a z-test for the population mean. Note that some conduct the z-test for mean simply because the sample size is larger than 30. The z-statistic for one population mean is given here. Substituting these values yields a test statistic of 2.36, rounded to 2 decimal places. Next, we set up a critical or rejection region for the test. Since this is a right-tail test, the rejection region will be in the upper tail here with an area of 0.03 representing the significance level alpha. Thus, the less than area is 1 minus 0.03 or 0.97. We can then use software or search in the less than z table for the closest value to 0.97. The closest to 0.97 here is 0.9699, indicating a z-critical value of 1.88. In essence, we should reject the null hypothesis if the z-statistic or z obtained is greater than the z-critical value of 1.88. This is called the critical or rejection region. Since our calculated or obtained z of 2.36 is greater than the critical z value of 1.88, we will reject the null hypothesis or say the result is significant. We can also use the p-value approach to determine the significance of the result. The p-value represents the probability of obtaining an observed effect or more extreme results, assuming that the null hypothesis is true. In this context, the p-value quantifies how likely it is to observe a sample mean of 32 minutes or more, if the true average is indeed 30 minutes or less. The p-value is represented by the area from the test statistic to the tail in the direction of the alternative hypothesis, that is, the upper tail in this case. Looking up 2.3 under 0.06 in the less than z table, we find the less than area to be 0.9909. The greater than area is therefore 1 minus 0.9909, which gives 0.0091. The p-value for the test is thus 0.0091. That means there is only a 0.91% chance of observing a sample mean of 32 minutes or more if the null hypothesis were true. We apply the p-value as follows. If the p-value is less or equal to the significance level alpha, we reject the null hypothesis. Otherwise, we fail to reject it. Since this p-value is less than our alpha of 0.03, we reject the null hypothesis. Equivalently, we say the result is significant or that the mean is significantly greater than 30. In other words, we reject the claim that the average user exercises for 30 minutes or less per day. Therefore, there is enough evidence to conclude that the average user of the app exercises for longer than 30 minutes per day. That is, we conclude that the app's claim is incorrect. Now, suppose variability increased so that the population standard deviation becomes 8 minutes. Substituting that in the Z formula results in a smaller Z statistic of 1.77. Recall that at alpha equals 0.03, the critical or rejection region for this right-tail test is Z greater than 1.88. Since this new obtained test statistic is not greater than our critical value of 1.88, we fail to reject the null hypothesis. And we cannot conclude that the mean is greater than 30. That is, we cannot conclude that the app's claim is incorrect. Again, let's verify our decision using the p-value approach. The p-value will be in the upper tail of the test statistic since this is a right-tail test. From the less than Z table, the area below Z equals 1.77 is 0.9616. Subtracting that from 1 results in a p-value of 0.0384. This p-value is not less than our alpha of 0.03, indicating that the null hypothesis should not be rejected. That is, the result is not significant. In essence, we cannot reject the claim that the average user exercises for 30 minutes or less per day. Or we have insufficient evidence to conclude that the average user exercises for more than 30 minutes per day. Finally, recall that we rejected the null hypothesis when the population standard deviation sigma was 6, but we failed to reject the null hypothesis when sigma equals 8. The standard deviation reflects data variability. Lower variability makes it easier to detect significant differences between sample and population means, potentially leading to rejection of the null hypothesis. Higher variability, that is, a larger standard deviation, can obscure these differences, often resulting in failure to reject the null hypothesis unless there is a substantial difference between the sample mean and the population mean. And that's it. Thanks for watching.